to the organizers. I really appreciate it. So the first part of this talk will be a slide talk. I hope you can see shadows. So everything I'll talk about today is joint with John Francis. It's a theorem of 3 parts. And to contextualize this theorem, it comes from a larger program of proving the cobordism hypothesis. So if you know of the cobordism hypothesis, you'll know that it's a coherent, continuous source of manifold invariance. Continuous in the sense that the invariants depend continuously on diffeomorphisms of manifolds in a suitable sense. That comes just from where the input is higher categorical data. So you could, given how the most basic manifold is Euclidean space, you could wonder what is the higher categorical connection to just Rn? Well, we, in light of, so not just Rn, but diffeomorphisms of Rn, and through like Graham-Schmidt, the topological group of diffeomorphisms of Rn is homotopy equivalent to the orthogonal group. So that arrives us at just the ponderance. What is the higher categorical connection between the orthogonal group, or of the orthogonal group? And that's what this talk is about. And this is where the crux of our approach to the cobordism hypothesis lies. So that's the context for this 3-part theorem. The first part says that the Bruhat cells determine a stratification of the orthogonal group. So to me, a stratification is a continuous map from a topological space, in this case the orthogonal group, to a partially ordered set, which I'll explain later in the talk. And it's not just any old such map, it satisfies suitable regularity. So each stratum, in other words, each preimage of an element here, is not just the subspace, it's locally closed, of O of n, but it's a smooth submanifold. And also the links between 2 strata has a smooth structure as well. That's useful for doing inductive arguments. So it's the Bruhat cells determine a suitably regular stratification of the orthogonal group. That's the first part. The second part is that, well, you could wonder, does this stratification respect matrix multiplication? So does it define a group object in stratified spaces? A moment's thought reveals that there is no non-trivial such examples, because translation in the group shows that a neighborhood of any point is isomorphic to a neighborhood of any other. So that's the wrong question to ask if it defines a group object in stratified spaces. But here's a sense in which it does inherit some kind of multiplication rule, this stratified object. Namely, to each stratified space, there is an infinity category associated to it, the exit path infinity category. An object in this is an element in the topological space. A morphism is a path in this topological space that only exits deeper strata into less deep strata. Informally, it's a subcategory of the path category. And this category is an associative algebra, not in categories, but in a weaker notion of categories, namely correspondences of categories. So this category that I'll indicate imminently is designed to articulate a sense in which matrix multiplication defines multiplication rule here. And really, it's the fact that matrix multiplication does not define a map between stratified space, but a very nice span, correspondence of stratified spaces. So what is this category in which this exit path category is an associative algebra? I'll write it without the red first as core for correspondences. An object is an infinity category. Think of this just an ordinary category if you want. And a morphism between two is a bimodule, by which I mean a functor from the product of the opposite of the source across the target into spaces, called a bimodule M. And in fact, the span that is needed to witness this as an associative algebra therein is not any old span, it's nearly left representable. So a little bit weaker than being left representable, in other words, for this bimodule to be implemented by a functor from C to D, is that, that this colimit is contractible.
What color is that?
Huh?
What color is that?
The color is red.
Can you just
What did you say?
G and D? Lowercase.
Oh, it's a, yeah. You fix an element of C, and you take the colimit of the bimodule over the remaining. Okay, so now that this is an associative algebra, this stratification of the orthogonal group is an associative algebra in a suitable sense. We could wonder, well, we investigate it, and here's finally the connection with higher categorical data between the orthogonal group and higher categorical data, and that's that this associative algebra acts on the infinity category of infinity n categories. And it acts on that in the only way that is appropriate given where it's an associative algebra, namely in this category of correspondence. Furthermore, that action is given by, or implemented by taking adjoints. So this is a peculiar type of action of something. It's some kind of like a lax action, as we'll see just right below. So let me contextualize how this action, just where you might have seen it in other places in the literature, or just in your own mind. So first off, Z mod 2Z acts on one categories by taking opposites. Z mod 2Z to the n acts on n categories by taking opposites at each categorical tier. And by reflections, Z cross to the n, Z mod 2Z to the n, is a subgroup of On, and this action of 3 extends that action that you all say no. But really this corollary, or this part 3 is designed for this corollary, which is that the topological group, no stratification, acts on the infinity category, not of infinity n categories, but the full subcategory of that, consisting of those infinity n categories, for which each K-morphism has both a left and a right adjoint. So that's, this is the sought-after corollary.
So, Damon,
Yes?
as a consequence of 3, you have this coalgebra structure of constructible sheaves on ON.
Uh-huh.
Oh, actually, as a consequence of 2.
Yeah.
Does this have a known name?
Yeah, it's the like Hecke, like pull back, push forward structure on sheaves
No, but
from double cosets of the maximal parabolic. Yeah, so there's linear instances of this that suggest that it should exist. I'll try to contextualize that a little bit later. So let me just indicate what this action sort of looks like in the case where n equals 2. So just restrict to the connected component of the identity, SO2. And that exit path category is really simple. It's just this coset. So there's 4 objects, and they're related in the way I just indicated. So we could wonder then, what's the orbit of this action on a given 2 category? And that's given in this way. So here's the orbit. Given the 2 category, you can take its double opposite, the opposite in both categorical tiers. You can adjoin left adjoints to every single one morphism in it. Likewise, adjoin right adjoints. And there's these canonical morphisms between 2 categories, given like this. and also given like this. That's the orbit. So that doesn't look too surprising. And furthermore, I want to, this might be familiar to you. For instance, if C already had adjoints, then if you adjoin left adjoints to every one morphism, it doesn't do anything. So this arrow is an equivalence, as are all of them. The result is an automorphism of C. That's the Serre automorphism. Sorry? Yes?
I think actually this picture, can you just explain a little bit more why exit SO2 is that picture? Or,
Yeah.
It must come from
Right,
the circle.
SO2 is the circle, right?
Yeah.
And that's the stratification of the circle.
So why is that the Bruhat decomposition?
Yeah, so it's the Bruhat decomposition of GL2 of R intersected with SO2. And it's not obvious, but it turns out to be that. And then the exit path category is this.
Can you just label the Bell group elements?
What?
Can you label the Bell group elements on Saturday?
Yeah. So the right. In this case, the Bell group is just sigma 2.
Yeah.
And actually, I'm going to come back to that when I explain this object. Yeah, remind me if I don't. Okay, let me just contextualize this
Sorry.
a little more. Please, yeah.
I assume I'm not the only one, but when you said it's a Serre, so I guess you could take C, for example, just the 0, 1, 2 cobordism category, and then you have all left and right adjoints. So what is the Serre?
Yeah. So in that case, it's the framed two-dimensional extended cobordism category. In that case, it's just the change of framing, the rotation of framing.
So S1 just access.
Yeah, by rotating the and then that's a good example because in the unframed cobordism category, like the unoriented one, that also has adjoints.
Yeah.
And there you see the Serre automorphism is trivialized.
Which is not obvious.
Well, that action is trivial. The change of framing action is trivial in that case.
That's true, but why this translates into that action is not so.
That's not obvious.
Fine.
Yeah. So we just noticed the Serre automorphism in the case where n equals 2, but given an n category, there's these two categorical tiers of time. So that means there's an action of SO2, but I'll write it as rotations in the coordinate plane spanned by the ith and ith plus first coordinates. So that's the group BZ. So that BZ action is codified as an action of Z on every Hom space compatible with composition, and that's just given by conjugated by the Serre automorphism in that two categorical tier there. A corollary of the method, it's not quite a corollary of these results itself, is an action of the group of base loops of the Grassmannian K-planes on R n plus k on the space of objects in any ek monoidal infinity n category, so long as it has duals and adjoints. That's relevant. So I gave an example here, which I think I'll just I'll utilize it as a slide talk and just let you read that if you want. There's a familiar instance of that you might already be aware of. But a corollary of this corollary of method, as you take k to go to infinity, is an action of O of n on the space of objects of any symmetric monoidal infinity n category, so long as it has duals and adjoints. That's a consequence of the cobordism hypothesis, but this doesn't use the cobordism hypothesis. In fact, in our logic, essentially the cobordism hypothesis is implied from that. And one more instance where you might have seen these kinds of results in the past, this is the deepest instance I'm aware of, is there's a particular tree category considered by Douglas, Schomer, Priest, and Snyder. And they show that the serodomorphism on the fully dualizable subcategory thereof is such that when you do it twice, it's null. So for this 2-to-1 cover, in other words, as a map of spaces, there's a factorization like this. And therefore, there's a map from the free group on it through the James construction that's a homomorphism. And some rearranging of what the Hopf map is, there's a natural map like this. And this 3 extends that homomorphism in the case where n equals 3. So, end of slide talk.
So this is actually like a homomorphism with the same-
Homomorphism, yeah.
Homomorphism.
Yeah.
But there's no choice of models on the right, so that it would really be a map between classified spaces, or is it actually?
Oh, okay. So, I mean, it's a morphism between group objects and the infinity category of spaces. Does that address that?
Right, so it's a map between
Classified
Classified
spaces, a base map between classified
Right.
spaces. Yeah. Okay, so I'll take a moment to. I just find this so inspiring for why one would ever expect any results like I just erased, that I want to share that. So here's motivation. And what I hope to convey is that if you believe in the serodomorphisms, then it would be natural to guess this action 3 that I just erased. So suppose you believe in the serodomorphisms. Then what does that obtain for you? So that there's these maps discussed up there. So for each I, there's the serodomorphism gives a map gives a homomorphism like this. Therefore, you get a map from the co-product of these as groups, so the free product like this, just from serodomorphisms. But there's some obvious relations among these words. So this factors through relations. So obviously, I'll say, if I and j are far enough apart, then doing some serodomorphisms on the I part and then doing it on the j part agrees with doing it in the opposite order. So one relation is that the I and j so long as the distance between I and j is greater than 1. So that's one relation. Another is that, and this one is far more complicated, there's a relationship between adjoining adjoints in degree I, after adjoining adjoints in degree I plus 1, after adjoining adjoints in degree I, between that and adjoining adjoints in degree I plus 1, I, and I plus 1. There's a braid relation among adjoining adjoints that's definitely not trivial to see. So in light of that, then given a word in rotations in each of these coordinate planes, you can reorganize, you can always shuffle those words around so that the following is the case. So there's, so you can shuffle words to ensure that any can be presented as one with at most one letter in SO R1 less than 2. And then, so you can kind of preference else of 1 and use the braid relation to do it, so that's the case. And then you can do it again for else of 2, but it might get stuck. You might sandwich an else of 1 between them. So that you can ensure that there's at most 2 letters in SO2 less than 3, etc., to at most n minus 1 letters in SO n minus 1 less than n. So if you count how many letters there are at most, it's 1 plus 2 to n to that. So what we're witnessing is that this map between groups factors through a map of spaces. And now I'll just identify all of these with SO2. This factors through a map from just SO2 to the n choose 2, that's the count, through as a map of spaces like this. But now there's a little more that you get out of purchase you get from these relations. If there was no letter in here, if that was the identity, then there would be at most one of these, etc. So what is the result of quotienting this by that kind of stuff? And there's a wonderful map called Euler coordinates. From that to SON, it's just given by taking a product of all these things. And so that's suggesting that there's a factorization like this, which happens to be a group homomorphism. So I find that suggestive for even believing in an SON action altogether. And it also guides how to construct it. So at this point, I'll start giving more definitions. Yes?
Go ahead.
So is the way to see this braid relation actually just computing exit paths between two strata?
Yeah, that's one way of seeing it in the geometry side, and then that has to be compared in the adjunction data side. And it's that adjunction data that I find much harder. But you're right, this is the held among exit paths.
I have a, so,
Yes.
so that diagram up there, you're sort of modding out by antipodal points. So, when it factors for RP2, right?
Yes.
And then you, at the end, you get a group homomorphism from SO3.
Yeah.
So the relationship between the SARE map and
Yeah.
the SO3 is not sort of just an extension or something like that.
Well, what we're right. Yeah.
Remember Chris also talking about this.
Yes.
I mean,
That's right.
yeah,
Yeah.
I thought it was.
Yeah. This.
The SO3 action should extend the SO2 action, but this is.
Yeah, I hadn't really thought about that. I guess this map is I guess that's not the map.
Right. Yeah.
Right. Yeah, that's a good point. Okay, so let me start. Talking about item number 1 among the theorems. So that's the construction of the stratification of O of n. The first order of business is to stay with that coset AN is. So AN is, well, it's the z points of the algebraic group ON, or in other words, symmetries of the n cubed, or in other words, sigma n reach z mod 2. And this has a nice presentation when written like this. I'll call it the Bruhat presentation of rotations by 90 degrees. Li is rotation by 90 degrees in the I plus first plane, and then reflections, A1 to AN. And there's some relations that obviously I don't have room to write in there. And this is, so I told you I was going to give a post set, I just named a group. So we don't really care about the group structure, we want a post set structure. So with post set structure, generated by a concatenation of letters in this presentation, by just declaring the identity element in this group to be less than Li, and also greater than. So rotation squared is a pair of reflections. So So by declaring those relations, and then the rest come along for the ride. Now, that's a disappointing way of ever describing a coset by just saying what the generated relations are. So let me just draw some examples. So I won't draw A2, but I'll draw SA2. I think you can imagine what that is. SA2 is this coset. It has 4 elements, A1, A2, the identity, L1, L1, A1. And they're related in this way. So that's nice. So I already drew that picture. And then another example is this partial order, it extends the, you always have a partial order on file groups, and it extends the given by the Bruhat partial order, and this partial order extends the partial order that you already know exists on sigma n. Extends the Bruhat order on sigma n. And for n equals 3, that looks like this picture. There's the identity, there's the transposition by 1 and 2, the transposition by 2 and 3, the cycle 1 through 3, 1 through 2. I'm writing in cycle notation. So there's that contractible coset. This is some, A3 is some 8-to-1 cover of this contractible coset.
Like, am I supposed to know what the Bruhat order is?
Well, if you don't know, I don't expect you to know it. But if you do know, then that's for more context.
But it's something Googleable?
What?
It's something Googleable?
Yeah, that's right. Including much of this talk. So now what's the stratification? So what the poset is, what is the map from ON to this poset? There's several ways of describing this map, each that has virtues. So one way is, say, given an orthogonal n by n matrix, to assign the max in this coset, which you have to argue indeed exists, such that for all k, the determinants of the upper left k by k corner of the matrix, that inverse times A, is positive. That's one way of describing it. Another is that this is the unique phi such that A belongs to the maximal Borel, or the maximal parabolic. This is where, so it belongs to this double coset where B is the upper triangle, the identity component of upper triangulars. Another way of describing it is the result of row operation is record the pivots. Assign pivots after doing row operations, but only row elimination and positive scaling. No permutations, no negative scaling, and you record the pivots. And that defines the stratification. And because of this, these are what's already known as Bruhat cells. So in other words, this stratification, each stratum is the intersection of a Bruhat cell in GL and R, or is a connected component of a Bruhat cell of R intersected ON. I don't expect you to know what Bruhat cells are. So proposition, this is a really hard deduction argument, is that this stratified space now, right there, is conically smooth. and I don't expect you to know what that means, but it's that alluded to type of regularity. So I'll just draw a quick picture of what this looks like when n is equal to 3, and just the identity components. SO3, you know, is homeomorphic to RP3, so I can essentially draw it as a closed disk, and it's this is a pretty crappy picture. So that's the one skeleton of this stratification, and there's 8 2 cells, which are each squares that fit into this in a particular way that I won't try to draw. So here you can see the braid relation already. I should erase this board. Okay, so next, the next theorem, part of the theorem, was that matrix multiplication defines an associative algebra structure on these exit path category. So let me say a word on that. Let me give the motivating idea and then give a criteria for when that motivating idea can be implemented. So here's the idea. So we already discussed, so let's say in the abstract, let G to P be a stratification of a compact Lie group. And I'll just denote this as bold G. So there's a canonical map from G cross G, the stratified thing, where you forget the stratification. That's a map between stratified spaces where the codomain is trivially stratified. That's an instance of a refinement. And then there's the given multiplication rule in the Lie group. And you might hope that this lifts. But we already kind of argued that essentially that will never be the case. So there's the next best thing. Well, this has some stratification, so does this. The issue is that this map might not respect stratifications. So find a common refinement. You don't know that exists necessarily. Some kind of transversality type result that is needed. But if it does exist, you can find some yet further refinements so that their multiplication, the same map, does define an error like this. And now what we're looking at is not a map between stratified spaces, but like a span between stratified spaces. And optimistically, you would hope that that this is suitably associative in a category of spans, etc. And it is not. So that's why moving to exit path categories and looking in this category of correspondences is convenient, because the kind of failure for associativity is always it's associated up to a further refinement. That all collapses away in this infinity category. So, so long as it turns out this multiplication rule, or this refinement exists, then theorem part 2 is true. So what is the criteria for knowing when this multiplication exists? I'll sneak it into here. So proposition, this works. And by this, I mean the existence of that common refinement, provided this criteria for all pairs of elements in the group. So it's going to be a transversality condition. So you're expecting surjectivity on tangent spaces, and that's exactly what it comes down to. So you can always look at the tangent space of the product. There's the derivative of the map, of the multiplication map, like this. Here is the tangent space of just the stratum in which that element A times B lies. And there's an inclusion of vector spaces. Likewise up here, there's the tangent space at A of just the vector space in which little a lies. Likewise B. there's this inclusion, and the failure for this map is essentially equivalent to the failure for this composite map to factor through here. So why don't we take the base change, so take the pullback just in vector spaces, and the question is whether or not that resulting map is surjective. Is surjective. That's the condition. And when I say this works, just to prove number 2.
But is the refined stratification the one just induced by looking at the graph and triply stratifying the graph?
The graph, what's the graph?
Oh,
that's the graph.
of
Okay.
multiplication.
Yes, that's right. Yeah. So in other words, yeah, it's when that intersection is all strata involved in that intersection transverse to one another. So I'll just say that when I say this works, this relies on quite a bit of developments. So this is a consequence of 2 papers, one that's called stratified homotopy hypothesis. That's joined also with Nick Rozenblyum, as well as a paper called Vibrations of Infinity Categories that defines L-core altogether and gives it a universal property so that it's a manageable task to define a map into it, such as an associative algebra. So moving on to number 3. How's it? Any comments or questions? So for number 3, and if you remember, that's the construction of the action of O and on n categories. So our approach is in 2 parts. First is to construct a tangential structure on stratified spaces on which bold ON acts manifestly. And then is to embed n categories into sheaves on such. And then it's just an observation that that embedded version of n categories in sheaves on such is stable under this ON action. So first, construct the tangential structure for stratified on which ON acts essentially manifestly. And then second is to embed cat n into sheaves on such structured stratified spaces. This embedding is factorization homology. So toward the first point, what is the structure? Sorry about the shadow. If there's been people who figured that out, let me know. So there's this infinity category of finite dimensional real vector spaces and injections among them, where you give each Hom space a topology of steeple spaces. There's a natural functor from bracket n that puts at 0 through n into it that just selects out Euclidean spaces and inclusions among such as the first coordinates. There's an action the seam line 2 to the end, on this object over vectinge. It acts trivially on this category itself, but on this map, it reflects in each of the coordinate directions. There's another infinity category over vectinge. The slice category. There's the canonical projection like this, and let's call this something suggestively GR of n. It's an amalgamation of all Grassmannians, as I'll point out in a moment. And this tangential structure that we seek will be intermediate. I'll call it bold GR then. I'm not going to tell you what it is, but I'll just give shadows of it. So one feature is that it localizes onto GR of n. Another feature is that bracket n maps fully faithfully into it. So that's already somewhat notable. And then you're not reading that as such. Okay. On this is an action of this bold O of n that is essentially manifest, and it's compatible with this fully faithful vector, and that Z cross the n action. And on any slice category, automorphisms of the thing you're slicing acts on it. So O smooth only acts on this, and this is all compatible. That's a refinement, so that's a localization.
So I think of
What?
bold GRN is just a family of quarters of cubes.
So, as I erase, I'll say some words. So, let's look at the maximal algebraic torus in GL n of R. Okay, so the maximal torus is R cross to the n. The Weil group, sigma n, permutes that all around with the GL n of R. And now in O of n, that each of those maximal tori intersects just as Z cross to the n. So we get this bunch of Z cross to the n's permuted around one for every element of the Weil group. And this stratification of O of n is such that each stratum deformation retracts onto one of those copies of a maximal torus. I don't know if that was addressing your question. Maybe indicates more generally. There's like 17 ways of describing what the stratification is. Okay, so let me, I want to indicate what this is by just saying, not actually what that category is, but what its base change over BOK is, the full subcategory of just k-dimensional vector spaces. So over BOK, I'll base change each of these, and it looks like this. What are the points? Certainly. There's the Grassmannian of k-planes in Rn, because after all, the steeple spaces mod O of k is that. And then here is, all right, bold GR of n. And what is this? This is the exit path category. Of the Schubert stratification of the Grassmannian of k-planes in Rn. So this thing is some amalgamation of all the Schubert stratifications. Okay. Now for the second part, how do we define, how can we interpret these categories over vectinge as tangential structures? Well, to each stratified space. So let B be a category over this infinity category, vectinge. And for each stratified space, a B structure on it, call it something X on X, is, it's a, well, you know, if X was a smooth manifold, there'd be a tangent classifier for it, which would be a map from its underlying homotopy type, or space, into BON. And likewise, given any stratified space, there's a map from its stratified version of underlying homotopy type, path category. In other words, it's exit path category, not into BON, but into vect-ing. This is classifying as tangent constructible bundle. And a B structure on it is a lift. So with this, then, we have a notion of such structured manifolds. We call them Bruhat structured manifolds, or stratified spaces. So this is a premise of defining a category whose objects are, right, in this second item, we wanted to embed categories and sheaves on such. So what is the category of all such structured manifolds? So there's a category, CMFD, upper B. C stands for compact, MFD for it's to evoke manifolds, upper B for the tangential structure, is an infinity category. It's the infinity category. Classifying proper constructible bundles. With fiberwise B structure. So the proper has to do with this compactness. And I just named everything after here. All that names not an infinity category, but a stack on the category of stratified spaces. And it turns out that that's a fine way of naming an infinity category, and that's the content of that first result up there. That one way of defining an infinity category is to name the stack on stratified spaces and then check that it satisfies certain properties. This was more or less the most economical way we could have managed for defining this infinity category altogether. So an object, so explicitly, an object is just is a compact stratified space with a B structure. And a morphism between two is a proper constructible bundle over the one simplex with a fiberwise B structure. Saying it like that, I think, evokes what a two simplex in this complete Siegel space is.
When you say bundle, you mean manifold bundle?
I mean a constructible bundle. So it's a map between stratified spaces with the feature that when you base change over each stratum in your base, the result is a fiber bundle of stratified spaces. And also a little more about what happens over links. So it's like all the degeneration of the topology in the fibers happens commensurate with the stratification of the base. So for example, here's a constructible bundle over this stratified space. You see this, if you base change over each stratum, it's a fiber bundle. But certainly it's not all total a fiber bundle. This cone gets pinched. I'm going to erase that. Okay. Now, inside of here is a subcategory of not just triangulations, but like triangulation or of stratified spaces, but triangulations of manifolds. So inside of manifold B is C disk upper B, and B here was each of the three options right there. So if you know what that is, so what I indicated is each a full subcategory of the respective versions of this is generated by disks in a certain sense. again, think of these as triangulated manifolds. This is localization that is fully faithful. And there's a theorem, just the content of the paper of factorization homology 1, which establishes, finally, is the connection to n categories. It establishes a fully faithful functor. I guess call it rho in case I use that letter again. From theta n, which is a category of n-ordered, finite, non-empty, linearly ordered sets, into disk n. So this is fully faithful. That's a remarkable fact because it's essentially saying that the frame automorphisms of a triangle is contractible. So the kind of regularity in stratified spaces here is really essential to establish this. Now so from this, it is then possible to obtain a pre-sheaf on theta n. So for each object, think disk or even triangulated manifold, and each of these, so I'll do blank for any of those three, there's this pre-sheaf, C of D. So it's a functor from theta n top the spaces, given by assigning to one of those the space of morphisms in D of the appropriate type from the image of this T of theta. So hom and disk blank from D to rho of T. And this is an infinity n category. A la Resk's definition. So finally is this connection to from this geometry to n categories. And factorization homology, the theorem of that paper up there is that factorization homology defines a fully faithful functor into sheaves. Into the bold GR of n. And it's given just by right con extension along this composite. So the theorem is that that right con extension is fully faithful. So there's our embedding of n categories into sheaves on such structured manifolds. Now, for the last little bit, let me indicate. So I'll just say it's an observation. It's not hard that this image is stable under the ON action on sheaves. What is not clear at all is that that action is implemented by adjoining adjoints. And so now let's see that. So theorem 3, which is that this action is given by adjoints, is implied by showing what turns out to be a canonical morphism between infinity n categories from the K cell, adjoining adjoints degree. So what is phi here? Phi is an element in A of n. And in that presentation I was indicating before, there's a canonical Bruhat presentation in the letters Li's and Ai's. And you know how to adjoin to any n category, such as the free K cell, adjoints in degree I, and you know how to take its opposite in some degree I. So thereby making sense of this. This is the result of, in the order of the Bruhat presentation, adjoining adjoints and taking opposites according to that symbol phi. And there's a canonical morphism from that, it turns out, to this value on the K cell with the Bruhat structure that's determined by phi. And it's to show that the canonical morphism is an equivalence. That's what it all comes down to. And this is the program for showing this is by induction. On n. So when n is equal to 2, as the base case, there's only one interesting case on the left-hand side, and that's C1 adjoint adjuncts in degree 1, in other words, the walking adjunction. And there's a map from that into D1 with the only kind of exotic framing, also exotic, the only one not coming from here. And this is an equivalence by inspection. Because you can say what this is explicitly, using the fact that essentially two manifolds are such that the loop spaces in them are always zero types, except for the sphere. And this, you know this explicitly by work of Emily, Real, and Verity. So that's a base case. What's the inductive step? So this inductive step is pretty much where we got stuck for a long time. And we had various ideas, and the key, it was mostly an organizing tool, I think, that we were missing. And the answer was recalmats. So, namely, there's a recalmat, not in the classical sense, given by two categories and an exact functor between them, assembling into a larger category, but rather one category for each permutation. So there's a recalmat indexed by the permutation group. Recalmat. So there's a sense in which you could say that sheaves on is stratified in the sense of recalmats by sigma and the permutation group on n things. How does that help? Well, it's stratified in such a way that each stratum is just a copy of of this type of structure. So it's stratified in such a way that each stratum is just a copy of infinity n categories. With each stratum, so each term in the recalmat sheaves on, so isomorphic to this at least, on that, which fully faithfully receives a functor from infinity n categories, remember. And it turns out that's actually even an equivalence. So each stratum is a copy of infinity n categories. Remaining is to know what these gluing functors are. So with gluing functors, so there's one gluing functor for every relation in this coset. And the relations in this coset, here's the key, are generated by length 1 relations. So to know what the gluing functors are in general, you just have to know what the gluing functors that bump up in the Bruhat ordering of this by 1. With gluing functors for the shortest gluing functors, in the sense of the Bruhat ordering, with gluing functors given by the n equals 2 case, and that's where the induction goes, given by the n equals 2 case. So that's more or less the inductive step.
Why isn't there like higher coherence?
There is, and I just didn't say that. There really, really is. Okay, I promised to give you an indication. I said it's in progress. So those coherence things essentially appear because of that braid relation. So we believe that it comes down to the n equals 3 case to manage those coherence things. And we've pinned down the n equals 3 case, and it's just, and that's where we are. So there are higher coherence stuff. In fact, in a recent paper with Aaron Mazelke and Nick Rozenblyum, we are developing recalments in general as a way, for kind of other reasons, for stable homotopy theory and cyclotomic spectra, for how to manage those coherence issues when the poset is not necessarily a linear poset. So there are coherence issues, and we don't know how to manage them yet. That's where we are. Thanks for your attention.
What happens when n goes to infinity?
I guess it's just infinity categories. But it's not like I have a prior definition of that besides that. So. While this n can go to infinity, the bold GR of n does not, there isn't a sense in which that goes to. Adjunction data is context dependent on which degree of category level you're working in.
Questions?
If not, we should thank you again.